Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. A while ago, I showed you in a video that I started to experiment with Texas Instruments DC-DC converter integrated circuit just to see what results could I get, especially when building handmade PCB at home and using just regular components, more or less, um, just because I was curious about the results. And the results were not bad, but to me, they were not quite satisfactory. And this video was presented to you about 2 months ago. It's called Step Down DC-DC Converter with the TPS 563201, a first experiment. In today's video, I would like to basically continue first by changing a couple of capacitors to see if this ripple, which was around half a volt back then, to see if this ripple could improve, and then to move on to other boards and to see what other results we got by using the same IC but on a different board with different components, as well as two more ICs, also DC-DC converters, and well, yeah, see what results do we get from them. The whole motivation behind me trying to create DC-DC converters at home handmade was that I simply was not satisfied with what I could buy on the market, on the local market here in my country. I did buy a few of them in the past and tested them, and I was not satisfied at all. The reasons were several. Even though the prices were very good, they simply did not perform well enough. The ripple was too high on the output, and or they would overheat, and or they would not be able to reach that level of maximum current that they stated they should. So overall, I was just disappointed with them. Now, the whole idea in the long run is to learn how to design our own DC-DC converters and switch mode power supplies in general. But it's still gonna take a while until we get there, or at least until I get there, until I manage to learn everything that I need. And until then, I just wanted to see if I could just take a look at the datasheet of a certain chip, take a look at the recommended schematics, and what would happen if I would just create one of those recommended schematics. Would they work? Would they work well enough? Or perhaps would they work very poorly and they would need improvements, and so on and so forth. So this is the whole reasoning behind these experiments that I've made, and some more that I will definitely make in the future. Now, last time, again about 2 months ago, when I created the circuit, I decided to do it by hand completely. This time, in order to make my life easier, I decided to just order some PCBs. I decided to just design the PCBs myself, but have them manufactured professionally by a company, and yeah, because that would just make my life easier right now when I just want to experiment with one chip or another, one component or another. So fortunately, PCBWay, which is sponsoring this video, was kind enough to help me get these boards done so that I can have my life easier. Therefore, before we move forward, and I'm gonna have quite a bit of things to show you and to explain to you, allow me to speak a few words about them in thanks for their work in creating these PCBs. So PCBWay, in case you did not know, it's a leading PCB manufacturer with many capabilities to help you build even most difficult projects. You can easily get an instant code for PCB manufacturing from the website's front page, upload the Gerber files, and have your PCBs created in just 24 hours. If you need more to get your project finished, they can offer PCB assembly services with manufacturer direct pricing, so you can have your PCBs delivered with components soldered on. Or if you do want to do the tedious work of soldering the components yourself, you can just order the CMD stencils and solder the components at home. Just finish your design in your favorite design software, upload all the necessary files to PCBWay, and you'll be contacted by one of their professional representatives after they manually review your project to make sure that your circuits get fabricated just the way you want. If you're building a circuit for a device that will need a case in the end, they can help you with that as well, offering you 3D printing or injection molding services to have your custom-made plastic case, or perhaps even CNC machining services to help you with a custom metal case. All you need to do is go to PCBWay.com, the link is in the description. Thanks a lot PCBWay for sponsoring this video and helping me create these boards that definitely make my life easier. And now let's get started explaining everything I've done and all the results that I got. Starting with my old board that was handmade. Now, back then, if you can see both in the left picture and in the right picture, you can see a couple of black capacitors. On the left picture, you see 3 capacitors. One is brown, 2 are black. On the right picture, you see only these 2 black capacitors. These were on the output, basically. And this nasty ripple, which was give or take half a volt, was due to these capacitors being just regular capacitors with regular equivalent series resistance, which were obviously not good enough for the job. So the first thing that I did, and you can see here, was that I basically removed them and I replaced them with a couple of ceramic CMD capacitors. I'm going to throw at you all sorts of components. I'm not trying to promote any other company. I'm just giving you codes and models to make your life easier, okay? So I decided to buy these 22 microfarads capacitors made by Samsung. This particular model, I'm not gonna read every letter. I'm gonna put in the description of this video every link to every product, just in case you want to buy them and you know, create these boards yourself, just like I did. So I figured, and one of you commented on my previous video that I should try X7R type capacitors, and I bought some of them. They are not cheap, but they're not expensive either. I mean, they're like 40 euro cents a piece if you buy 10 of them, 20 euro cents a piece if you buy 100 of them or more. So they are definitely accessible enough, let's put it this way. And I have replaced those electrolytic normal capacitors with these 2 ceramic ones, and yes, that did the trick. That was absolutely what I should have done in the first place. So let me show you just a second. The ripple basically got shrinked with an order of magnitude. Essentially, we jumped from having a roughly half a volt ripple to give or take 50 millivolts, so literally 10 times less. This is when drawing no current. This is when drawing a bit more than 100 milliamps. It's still around 50 millivolts. This is when drawing half an amp. But bear in mind that now we have jumped on 20 millivolts per division, so we have about 2 divisions, which means give or take 40 millivolts. This is an amp, and we jumped again to 50 millivolts per division, so we have about, I don't know, 60, 70 millivolts of ripple. Of course, we would need to ignore these very, very, very short spikes. Otherwise, the measurements on my oscilloscope say about 154 millivolts, but this is because these measurements take into consideration these spikes as well. I would say that these spikes can easily be ignored. The bulk of the ripple is found here in the middle, and it's like, I don't know, 70-ish, maybe 80 millivolts, but not more than that. And if we draw 2 amps from, again, we're still talking about this handmade board, to which I've just replaced the output capacitors, the ripple drops down again to around 50 millivolts. So this was clearly an improvement, and actually this was the solution. Of course, this made me happy enough that, now I know that, and by extension you know as well, that we can just create a PCB handmade at home and use mostly through-hole components. Provided that we use some very good output filtering capacitors, we will get a decent job. But I also decided to design a second board, which is this one, this smaller one, in the center of the picture right now. And I decided to basically use, of course, the same chip, the same control chip from Texas Instruments, but almost entirely just semi components and different kind of components. All the capacitor or the large capacitors have been used, these ones. So both output capacitors in this small board are the same that I've shown you before. But I've also placed the input capacitor the same, like this one, 22 microfarads multi-layer ceramic capacitor. In other words, I decided to not use an standard electrolytic capacitor because it just didn't make sense in my mind. Also, instead of this big coil that I bought, I decided to use a semi inductor that, of course, I also had to buy. And it is this one from Murata company. Still 3.3 microhenries, because this is the inductance that the datasheet of this chip tells us that we need to use. It only goes up to 1.9 amps, sadly, but I don't plan to use the boards at more than this. The chip himself can withstand 3 amps or can deliver 3 amps, but of course now my board can only deliver a maximum of, I would say, 1.8 to be below this 1.9 amp limit. Still good enough for me. If we buy 10 or more of these inductors, they cost about 22 euro cents. 100 milliohm resistance, which is pretty good, and it occupies a very small space. On top of that, I also decided to use semi-D resistors and only a couple of through-hole 100 nanofarad capacitors for Basically, let me see. One for filtering the voltage on the input, and another one for bootstrapping the switch that switches the inductor on and off. Other than that, I actually struggled, and I used only semi components soldered by hand. I have to admit that I'm really not a fan of semi components. I really hate them. But anyway, in the end, I managed to solder them. They're not very nice solder joints, but they work. Okay, at least for an experiment, they work. I don't know if I would keep doing this in the future, but I wanted to see, you know, what happens if I basically make a board that is literally half the size, and it's manufactured by you know, a company, properly manufactured. Granted, the design is still mine, and you know, I cannot say that this design was super awesome, but the results that I got were essentially the same. So this is now the ripple for this second board with the same TPS Texas Instruments chip. 20 millivolts per division, no current whatsoever on the output, and we see that we have the same, give or take 50 millivolts, which is good. Half an amp current drawn, still around 60 millivolts of ripple. 1 amp, about 30-40 millivolts ripple. 1.5 amps, again around 50-60 millivolts ripple. So this tells me, these two experiments tell me that one, semi components do help, but we don't need to go overboard and just use only semi components. We can use through hole as well, provided that we are careful about at least the filtering capacitors and ideally the inductors as well. Two, this also tells me that I can easily just design and build a PCB board at home myself, not a problem, at least with this IC. The only difficulty is in soldering all the 6 pins of this IC carefully enough so that we don't short circuit something, because then it won't work. Anyhow, maybe we could improve the ripple somehow, but at this point I really don't know what I could do. With this board, I think I made everything that I could potentially do. You know, it's a smaller board, it got only semi components. I don't know if I could improve the ripple even more, but honestly, at this point, I don't care. I declare myself satisfied. Now, moving on, I wanted to test a couple of more chips. I know that basically some of you will say that the 34063 is very old and relatively inefficient. And yes, you may be very well right. However, for me, it's relatively new, because I just found this chip, I don't know, a month ago, give or take, or 2 months, something like that. So I haven't played with him so far. I wanted to see what he can do, and honestly, to me, he sounded pretty promising. And why is that? Well, because it's got just a second, please, to open the datasheet. It's got a whole bunch of pins that are exposed to the outside from all points of the internal circuit, and to me this means that it wants to give me the flexibility to do all sorts of things around this chip and to potentially improve the efficiency, you know. So this was definitely a chip that I wanted to play with. Now, this 34063 comes actually in different variants based on what manufacturing company produces this chip. I bought two of them, but I only tested one, which is MCHE 34063, manufactured by SETE Microelectronics, if I remember. Yes, by SETE Microelectronics. It's a pretty cheap. I mean, it sounds weird, but it's a pretty cheap integrated circuit. Only 50 cents a piece for 5 pieces or more. It can be even cheaper if you buy several pieces of this. Personally, I'm not a fan of this particular model being a SEMEDE version. However, it's a small outline 8, so 8 capsule, so it's definitely a lot easier to solder than, you know, the Texas Instruments one. You might find different other versions of this particular model that comes in through-hole version. I couldn't find back then on the market, so I couldn't buy it, but I did find some second-hand chips from a radio amateur, and I did bought a few of them. So yeah, in the future I will definitely work with those a lot more than this SEMEDE version, but nevertheless it matters less. I went into the datasheet, I took the recommended version of schematic for a step down converter, and I pretty much implemented that version as she was in the datasheet. The only thing that I changed was that I had to use two Schottky diodes in parallel because I just did not had at that time Schottky diodes that can pass more than 1 amp. And because this chip says that it can handle 1.5 amps, which, spoiler alert, doesn't really handle, at least not by himself. Maybe with the help of an external transistor, I don't know. But anyway, I wanted this circuit to be able to resist 1.5 amps, so I needed to place two diodes in parallel here. But other than that, it's pretty much just the standard datasheet circuit. 100 microfarad capacitor on the input, that's just a standard electrolytic, nothing fancy. On the output, I did try several capacitors just to see, you know, the difference, and I will show you the results in a moment. For the inductor, I decided to buy an inductor instead of, you know, actually trying to wind my own inductor. Maybe in the future. I chose this DPT 220A5 made by Ferrocore, 220 microhenries. It can resist up to 5 amps, 110 milliohms wire resistance, which is low enough, so theoretically we shouldn't expect many losses. The price is considerable. €2 a piece if we buy 5 or more. It's not super expensive, but again, it's not cheap either. And yeah, and I did some tests, and this is the circuit that you see here. The output capacitor is missing because I desoldered him and used him here in this other model that I will show you in a moment. There are only two weird things that you might be able to see here. First, these three resistors placed in parallel. This is because I I discovered that I don't really have a 0.33 ohm resistors. he needs a shunt resistor to basically measure the current through the inductor. And yeah, I just had to take 1 ohm resistors, place 3 in parallel, and this is how I got my 0.33 ohm resistance. The other weird thing are these 4 wires here that are actually connected together. This is because, like I said, this chip does, in my opinion, provide a high level of flexibility, and it has certain pins that normally they are supposed to be connected together. But I will want in the future to play with them and connect them differently, like perhaps an external higher power transistor, and so on and so forth. So instead of, you know, connecting all of these pin 1, 8, 7 and this shunt resistor together by default, I decided to just output them individually on a wire each. And in these tests, I just connected these wires together. But in the future, I will be able to disconnect these wires and connect them separately in different ways and perform some more experiments with this board. Because again, I found this chip to be this integrated to be okay-ish. The efficiency was a bit below, generally speaking, below 80%, but not by a lot, like between 71 and 83%, depending on various cases. Now, regarding the output capacitor, which, like you can see here, it is missing, I actually changed him 3 times and I placed 3 different output capacitors, all of them having 1 millifarad or 1000 microfarads if you want to express yourself that way. But every time it was something different. I had a Nichicon that I recovered from an older device, and I placed him first. I performed some tests. I forgot to mention, I made this board to output fixed 5 volts voltage on the output, and on the input I was feeding this board with about 12 volts, as with all the other boards, just to have more or less uniform test all across the board. I was using an artificial load to pull some current, and I was varying this current, you know, measuring input-output voltage, input-output current to calculate the efficiency. Anyway, and I was also looking at the output ripple, because this is what I cared about, to see, you know, if I change the output capacitor, how much will the output ripple be affected. And yeah, I can definitely say that there are some differences, but not that many. So with the Nichicon recovered capacitor, basically second-hand capacitor, I had 12 millivolt ripple on the output when I was drawing no current whatsoever, and up to 90 millivolts of ripple current, of ripple voltage, when I was drawing 800 milliamps of current. I couldn't go higher than 800 milliamps because the chip would go into protection mode. I'm guessing thermal shutdown or some form of thermal protection. At half an amp output current, the chip was very warm. Like he was actually kind of burning. I could hold for a while my finger on him, but it was starting to really hurt. So I would say he was at around, I don't know, 60 degrees or so. Of course, I'm talking about Celsius degrees, not Fahrenheit. Yeah, and also if we are to look into the data sheet at that particular circuit that I was basically creating, the step-down converter, it says that it's meant to give half an amp on the output, so not more than that. Okay, so yeah. Now, After this Nichicon capacitor, I changed him with, again, we're talking about the output capacitor only. I changed him with a Samwa capacitor that was brand new. And the ripple was more or less the same. 12 millivolts at no current drawn and 30 millivolts at half an amp. Yeah, okay, it's 10 millivolts less than with this Nichicon recovered capacitor, but meh, 10 millivolts less, I don't think it's all that much. And then I tried some Samxon low SR capacitor. Again, 12 millivolts at no current drawn and 25-ish millivolts at half an amp, so theoretically somewhat of an improvement relative to the other capacitors which were not low SR, but again, not that big of a difference, you know. The low SR capacitor used was either this one or a model that is very, very, very close to this one. Okay, 23 euro cents a piece if we buy 10 or more. Anyhow, all in all, I would say that this chip, this 34063, is nice and promising. Perhaps I will be able to hack him by, you know, connecting some external components and maybe bring his efficiency up a bit. I will definitely play with him more in the future. Last but not least, I wanted higher power integrated circuit to build a DC-DC converter to see, you know, how much can I obtain. And again, I have a little bit of an obsession for the ripple current on the output, because realistically speaking, I find that to be the most important problem. So I chose an LM2576 chip that is high power 3 amp chip, the so-called simple switcher ones from Texas Instruments, but nowadays they are being manufactured by other companies as well. And as a matter of fact, this is exactly what I chose. Taijin technology, LM2576, because really the price is much, much better. If we go at Texas Instruments and take a look at their prices, we will see that, first of all, they're much more expensive, like 3.5 euros a piece, the smallest price. And the other thing that I just don't understand why they do it, this other company doesn't do it, but Texas Instrument for some reason does. Fixed voltage versions of this chip are cheaper than the adjustable version. So if we take a look at 5 volts, 3.5 euros, 12 volts, 3.6 euros, pretty much the same, right? 15 volts, okay, this is a bit higher, it's 4.3 euros, but anyway, adjustment version 4.3 euros. So between 4.3 and 3.5, there's a significant distance, I would say, significant difference in price. So I don't know why they would do this, because realistically speaking, even in their datasheet, they clearly state that the only difference is the fact that the adjustment version doesn't have two resistors that form the feedback voltage divider, whereas the fixed version integrated do have those resistors, and those resistors have a certain value in order for the chip to regulate the output voltage at that particular voltage, you know. So from a manufacturing point of view, there's no difference. Why do they want to make the adjustable version more expensive? My best guess is only for marketing purposes. which I totally hate. Now, when we take a look at datasheet technology components, again, I'm not trying to promote them in any way, but first of all, they have the same prices all across the board, no matter that we're talking about the adjustment version or the fixed voltage version. And like I said, they are much cheaper. 1.3 euros instead of 3.5. I would say it's almost 3 times as cheap, you know. So anyway, I bought a 3.3 volt output version chip because I just assumed that the adjustable version is more expensive. I then later found that this is not the case, but anyway, I got a few pieces of the 3.3 version chip, but any fixed voltage chip can be modified, not internally but externally, to output any other voltage that we want. Of course, any other higher voltage. We cannot make him output a lower voltage, but we can make him output a higher voltage by just using one resistor in the feedback. Okay, instead of tying the feedback directly. So normally when you have a fixed voltage version and you want that voltage on the output, you just tie this feedback, the pin number 4, which is the feedback pin, directly to the output. And the chip will do the regulation himself. You don't need these two resistors at all. When you have the adjustment version, then you need to put both of these resistors here and read in the datasheet what's the formula that will give you the output voltage based on the value of these two resistors. Anyhow, you can use a fixed voltage output integrated in order to have a higher voltage. You only need to place this upper resistor, R1 in my case, and you will, based on how small or how big this resistor is, the chip will essentially increase the output voltage accordingly. So this is a nice trick to know if you still want to buy Texas Instruments components, but you don't want to spend more money for those adjustable versions, because there's no point. You can buy the cheapest, lowest voltage version and place an extra resistor in your circuit, and that's it. Okay, now other than that, the whole schematic is super simple, even simpler than on the previous chip that I've shown you. We have the same 100 microfarad standard electrolytic input capacitor, one or more diodes. Again, I chose 2 in parallel because I wanted to go up to close to 2 amps, and I just couldn't. I didn't have the proper diode, but anyway, you can just pick a better diode and just place one on your board. 150 microhenry inductor, although in their datasheet they specify only 100 microhenry inductor. I did not have the 100 one that can go up to 3 amps, which is the maximum current of this chip. So I chose a 150 microhenry. Generally speaking, choosing higher values of inductances should not cause big problems, at least if you don't go overboard by a lot. So I chose this particular model, which can go up to 3 amps. I'm not gonna go up to 3 amps, even though the chip can, the inductor can. I'm gonna go up to only 2 amps in my tests. 120 milliohms is again a good enough resistance that will not cause a lot of losses. The price is meh, 1.5 euros for a piece if we buy 5 or more, but it's not super expensive either. So it goes. I placed 2 output capacitors just so I have 2 places on the PCB, but in the end I chose only one. I used only one capacitor. And I used essentially two of these that I used in this previous model. I first made some tests with the Nichicon recovered capacitor, and then I swapped him for the Samson low SR, and these are the results for the LM2576. The efficiency was definitely better than 34063. It was above 80% pretty much all the time. I've encountered only a 60-ish percent at very small output currents. I guess this is normal, but you know, after half an amp or so, efficiency goes up to 80 or above, 80% or above. The ripple was nice enough. I mean, I can't complain. It's comparable with the other models that I've shown you before, the other boards, the other experiments that I've shown you before. 10 millivolts at no output current whatsoever, and then about 35-45 millivolts peak to peak, pretty much irrespective of the output current that we're drawing from the circuit. What can I say? When I changed the output capacitor for the low SR one, I did seem to experience a bit of an improvement. Like, instead of 40 millivolts for half an amp, I got about 25-ish millivolts for half an amp. Instead of 40 millivolts for 1 amp, I got only 30 millivolts. And instead of 45 for 1.8 amps, I got only around 40. But really, the differences are not that big. So yeah, all in all, I am definitely content with these results and with my experiments. Now, that's not to say that you know, maybe we could place even better capacitors on the output and get even smaller ripples. I don't know, it may be possible, but I personally don't care at this point for more. So my personal conclusions are that one, this particular TPS model that I've made a video 2 months ago is nice if you want a maximum of 7 volts output voltage, 3 amps output current, although that's pretty nice anyway, and if you don't have a problem working with CMD components. The other conclusion is that LM2576 is definitely a good choice when you want a high power, simple to create a DC-DC converter. Well, high power, relatively speaking, goes up to 3 amps. And when you want to just not be bothered with all sorts of details about, you know, how to do this, how to do that, especially when you already have the inductor and the capacitors, perfect. One more conclusion that I would draw is that this 34063 model could be a good choice for the future once we learn how to basically how to improve him by adding extra components on the outside. That might make him you know, improve his efficiency, and yeah, overall provide us with perhaps even better output ripple. Anyhow, it's definitely an option that you shouldn't jump from the very beginning. You should just study it and then draw your own conclusions if you want to work more. Personally, I will definitely study this chip a bit more. I will want to add some more components and see how I can use this chip better in the future, so more experiments will definitely come. Thank you very much for watching. Before I go, Perhaps it would be useful if I go very quickly through the Ripple print screens of these two models, 34063, because I've shown you the TPS ones, but just to show you how the Ripple looks like, not just a simple number, but how the Ripple looks like. 34063 when there's no current whatsoever, when we have 200 milliamps of current, 500 milliamps, 800 milliamps, but I should have zoomed in a bit more. And this is still 34063, but with the other capacitor, no current whatsoever, half an amp, low SR capacitor, no current whatsoever, and half an amp. So as you can see, low SR at half an amp. And so yeah, so the Ripple has basically two components, these very short spikes and this triangle form lower frequency Ripple. Anyhow, LM2576, 0 amps with the Nichicon recovered capacitor. I've zoomed in quite a lot here because I was curious to see, you know, what do I have. And yeah, based on the fact that we have 50 nanoseconds per division, you can easily deduct from this image that there is some high frequency content in this Ripple, like in the order of megahertz, tens of megahertz. Anyhow, 100 milliamps of current. We have a more predominant lower frequency Ripple, also triangle wave with very small spikes. 500 milliamps, 1 amp, 1.4 amps, 1.8 amps with a Nichicon recovered capacitor, now with Samsung low SRU, 500 milliamps, 1 amp, and 1.8 amps. And that's pretty much it. So I hope now you know a little bit more about these chips and these switch mode power supplies, well, these DC-DC converters to be more precise. Thanks a lot for watching, and don't forget to like and subscribe if you would like to see more. Like I said, I definitely plan to do more experiments in the future, so yeah, subscribe would definitely help the algorithm share my videos to other electronic enthusiasts. Thanks a lot for watching. I will see you next time. Bye bye.